like, oh, dude, this is good.
That's better. We just have one big idea left to deal with before we're ready for that final exam. And you'll remember that the final exam is not really a final exam. It's the last midterm. It will not be cumulative, but in order to work some of these problems, you need to understand circuits, because even though it involves an inductor, it's still a circuit. The reading assignment, chapters 19 and 20 just mean you should go back and review. But if you look at the reading quiz for Tuesday, the quiz asks if you would like 5 free points, okay? But you've got to click yes or you don't get your 5 points, okay? You've got to do a part there as well. Howdy. We have homework solutions at the MAX site. We have solutions to 2 sample exams that are at MAX. Those sample exams are from Montana State University, where the final was a little bit cumulative. It was 2/3 on the new stuff, 1/3 on the old stuff. So if you see questions on there, about waves or about electric fields, just ignore them. Those won't be on your exam. Okay. Are there questions on the final exam? Yes, Thomas.
You have to know circuits for the final.
Today we're going to talk about circuits that involve an inductor, and so since we're testing you on inductors and circuits, yep. But that's part of you now. That's part of you. Like Physics 105 last semester, our class has been relegated to the Richards building for the exam down in room 144. It runs just exactly like the testing center. It's the testing center annex during testing week, and it'll be open all week long or all testing period long. Okay. Let's start with a prayer. Would someone be willing to offer us a prayer today? Thank you.
Dear Heavenly Father, we are so grateful that we could come together and learn and to learn from Greg. Father, please bless Dr. Francis that he may be able to teach us by the Spirit and that we may learn by the Spirit. Father, we're so grateful for Jesus Christ and his atonement in our lives. Please help us to access that power and that we may properly prepare for finals and for the upcoming things in our lives. Father, we're so grateful that we can study at this institution. And we say these things in the name of Jesus Christ. Amen.
Okay. Let's start with a really quick pop quiz, a very easy one. Which right-hand rule gives you the direction of the magnetic flux through a current loop? And I'll get you started here. Okay, now you can click.
Say I don't even. It's just like
Also,
That's,
so there's so.
The flux is NBA. And another one is just NBA.
Oh, that's the only math.
Math is so chill though. Something 950.
Okay, get your vote in.
Wow.
Good. Okay, most of us are on the bus. And then there's always this person, always with us. Okay. Well. There we go. Now it's working. Okay, the answer is C, right-hand rule number 3. You remember right-hand rule number 1 is the only right-hand rule that gives us a magnetic force, a push or a pull. And the other two are just memory devices. Right-hand rule number 2, we use when we've got current in a long straight wire. We use our right thumb, the straight thumb, to represent the current. The fingers tell us which way the B field, the magnetic field lines wrap around the wire. And right-hand rule number 3 is when we have a loop of current, we use the curved part of our hand to represent the current. Our thumb represents the direction the B field lines, the magnetic field lines are passing through the center. They also teach us which side of that current loop is the North Pole if we're replacing it with a little bar magnet. Now, a couple of days ago, we started talking about the idea of a generator. And we talked about the fact that anytime we change the number of field lines through a loop, we're inducing a current, we're generating a current. And so whether I change the number of field lines through this loop by bringing the magnet close and far away, or whether I just change the area that those magnetic field lines see by turning that coil in the magnetic field. That would also generate a induced current. Now, if we look at those field lines heading towards the open door there, when I have that coil like this, a lot of them are passing through the coil. Now none of them are passing through. Now a lot of them are passing through the other way relative to the coil, and then none of them. And so I'm constantly changing the number of field lines that go through that coil. And that induced current going around in a circle acts like a bar magnet. As soon as I start turning it, I get that current in at the bottom, out at the top. Remember the half donut representation. And if I use my right hand rule number 3, that gives me a little compass needle. It's a bar magnet, a dipole we call it, but it acts like a compass needle. And you know what that compass needle wants to do? The compass needle, like any other compass needle, wants to line up with these external magnetic field lines. But we're forcing it the other way. And that's going to cost us positive varric. That's going to be hard. And that's how we pay for this current that shows up. That current is energy. It has to be paid for. Now, as soon as we get to this point here, well, if the current stayed the same direction, this little compass needle would help the turning, would help us, would make our life easier. Is that the way the universe works, people? No or heck no? Heck no. And so as soon as it gets to this location, nature changes the direction of that current. Watch that again. It was into the board on top, and then pow, it's out of the board. And that changes the direction of the compass needle. So again, I'm fighting it all the way around. And when it gets to there, it changes again, and I keep fighting it. Okay? Now, right at the end of last Thursday's lecture, I asked you about an electric fan. Is that a motor or a generator? And we gave the answer as both. Okay. Now, it's definitely a motor because that's what turns the fan blades. And we generate that current with the battery. That battery current we can control with engineering. We can decide when the current's going to go into the screen at the top and when it's going to go out of the screen at the top. And we do that with the commutators, with the bushings, okay? But we always set up that current through engineering such that the dipole, the little compass needle, is anti-aligned with these magnetic field lines. And it's going to want to line up. And that's what turns the fan blades. That's what turns the motor, okay? And here's the thing. Whatever turns that motor, whether it's me or whether it's the battery current, that's a coil of wire turning in a magnetic field. And once it starts turning, there's going to be an induced current. And that induced current we just found is always going to fight the motion. So we have to pay for that induced current. Now, I want you to see that there's two currents going on. There's the battery current that we control through the commutator and engineering. And then there's this induced current that nature controls. We have no switch on that. That just happens through Faraday's law and Lenz's law, okay? Now, we call that the back EMF or the back voltage because it's always going to fight the battery voltage. It's always going to be trying to push current in the opposite direction. So I think of the total current in the coil of that fan as being the current that's driven by the power source, the battery, if you will, minus the current that's trying to be driven by nature, the induced current due to the changing field lines through our loop. Okay, and so watch what happens as this goes around. Remember, the red arrow is caused by the battery and it's causing the motion. The green arrow is caused by the generator effect, the back EMF, and it's fighting the motion. Okay, and once I get to this point here, watch what happens. We change the direction of the red arrow with our commutator, with our engineering. But the green arrow, nature takes care of. And watch here go, pow. And see how they change direction? Pow. And now the red arrow is going to keep turning the wheel, turning the fan, and the green arrow is going to keep on fighting it. And then I get here and pow, it changes again. Now, here's a sample question. I've got the coil of a motor that has a resistance of 4 ohm, and I plug that motor into a socket where the voltage is 120 volts. And the coil develops a back EMF as it starts spinning of 118 volts when it's finally gotten up to its final spin rate. The motor's turning a wheel. We don't care. It's turning something. So the question is, what's the current when we first turn on the motor? And then what is the current when the motor is operating at its normal spin rate? And so we're going to work that out real quick. It's really very simple. So before it starts spinning, when I first plug this in or first turn on the switch, I can use V equals IR. And when I say V, I mean change in V, the voltage difference. Before it starts spinning, there's no back EMF, and the total voltage is just 120 volts. And that's going to drive current through the fan, through the resistance of the fan, which is 4 ohms. And that's going to give me a current of 30 amps. Well, that's huge. That's a really large current. You don't want 30 amps going through some sort of device that's in your home. But it's only 30 amps for an instant until that thing starts turning. And then when we do V equals IR, now I've got 120 volts from the wall turning the fan, and I've got this back EMF of 118 volts, and that's driving total current through 4 ohms. And that's going to give me a total current of 0.5 amp. And that's what you want going through some household appliance, is 0.5 amp. Now, this is a feature, not a bug, okay? Because you remember from Physics 105 that when we get something turning, we have to provide a lot of torque to get it started. But once it's turning, it wants to keep turning. That's rotational inertia. It just wants to keep turning. And the only thing keeping it from turning at the same rate forever would be friction, okay? So when we first plug something in, I've got that huge current to give me a huge torque to get it turning, to get it started. But once it gets started, I generate this back EMF that allows me to just go at a constant velocity. It starts spinning. Let me back up. If there was no back EMF, I'd plug it in and there would be 30 amps that would just be spinning this thing faster and faster and faster and faster until it got to the speed of light, okay? But because there's this back EMF that depends on how fast it spins up to where the net current is just the right amount to overcome friction. And then it turns at a constant rate. At that point, you've got a steady state and it just keeps turning. Now, let me see if I can give you a visual of this. Our third child, the one that became the orthodontist and is filthy rich, as a child, it shouldn't surprise you to find out that he cared a lot about money, okay? And he would do any chore for money. And his mother and I felt an obligation as his parents to take advantage of him and put him to work and give him horrible tasks and pay him a quarter. And one day, I asked him to take the corded dustbuster and clean out our 1979 Chrysler Cordoba. I don't know if you know that car, but it was huge. It had a land yacht and it had a hood that just went on forever. And we couldn't open the hood because the cable that you pulled to pop the hood broke. And it was dangling behind the brake pedal. You know, it was terribly dangerous, but you know, they were different times. They were different times. So I offered Christian, my redheaded son, 50 cents to go and dust bust this car. So the next thing I know, I hear screaming out in the garage, and there's smoke, there's fire. It's just a mess. And what had happened is he had been dust busting, and the dustbuster had sucked up that metal cable that jammed the vacuum. And so all of a sudden, the coil that was turning stopped turning. And at that point, we lost our back EMF, and suddenly, instead of a 0.5 amp going through, we had 30 amps going through. And that dustbuster wasn't built for 30 amps, and it just burst into flames. Okay, and that's the way it's going to work if your hair dryer gets suddenly jammed. It's going to suddenly have too much current going through it. See if your neighbor understands back EMF. If not, slap them or do something.
Like, well, it's the back end is gonna have a
Yes.
Explain it.
We tensing up and getting ready.
Simple for 118.
What do you would do?
Okay,
I understand. Yeah.
To buy the old by the
another benefit of this is that you only pay the power company for the current that's actually running through that device. That'd be the half amp, not the 30 amp. And so this is a wonderful thing. Okay, moving along here. There it is. Let's do another pop quiz. When you drive onto a smart light detector in Antarctica, busy streets need smart lights. Does the current flow clockwise or counterclockwise with your clicker? And let me just remind you, before you click, if this is the coil that makes that detector that we're inducing a current in Provo, the magnetic field lines go towards Canada and down 70 degrees, okay? But this ain't Canada, okay? I mean, this isn't Provo. This is Antarctica. And in Antarctica, I mean, this is Provo here, where the field lines are coming down. But this is Antarctica here, and they stand on their head down there. And so the field lines would be coming up out of the ground, up out of the pavement. Are you seeing it? Okay. And so now with your clicker, you can answer, is it clockwise or counterclockwise?
You drag your.
Was it? We know the
That was.
Change on this. We go down.
Oh, you're right.
I think counter. That's why I don't.
So if you were driving right there where that guy is standing,
That's big.
Change, I don't know, because I'm thinking, understand, right, on Android. That's an intern here, that's gonna be that way. Like that. I know, same.
There you go.
You're.
go wrong. I don't know.
Okay, last call.
What is? I have no idea.
There we go.
Whoa.
Oh, okay. That's depressing. Not only is it depressing because we've got, we don't have agreement, but the right answer didn't even win, okay? The right answer didn't even win. So we're not ready. We are not ready for, the correct answer, of course, is clockwise. Now, folks, think about this. In Antarctica, the Earth's field lines come up through the pavement, okay? Because we have the magnetic field of the Earth down in what we call the South Pole, geometric South Pole, is the magnetic North Pole of the bar magnet. And the field lines come out of the north, wrap around and go into the south. And so the field lines due to the Earth are coming up through the pavement. But the Earth's magnetic field is fairly weak, just a couple of field lines. When you drive your car over that, the engine block of your car is magnetized. It has a net magnetic field that's aligned with the Earth's magnetic field. We found that we could magnetize iron by putting in a magnetic field, and that would line up all the dipoles in that iron, okay? And so when I drive the car up over this loop, I'm changing the number of field lines up from 5 to 55, okay? That's the change. Fight that change. It went from 5 to 55. How am I going to fight that change? Which way do I put field lines? Down, put them down, and do it with your right thumb, okay? And if your right thumb is pointing down, that's the direction of the induced flux. The induced current is given by your fingers, okay? And they're going clockwise. See if your neighbor got that wrong. You know what to do.
Yeah. If you expect it to change it down, but if you're like, lines are coming out at you.
It's the direction the Earth's magnetic field is going. Yeah.
But if,
Yeah.
Yeah.
each other, like, yeah, it's like.
Okay.
Yeah.
The question was just asked, does the car always line up with the field lines at the location? And the answer is yes. In Provo, the field lines due to your car's engine are down because that's what the Earth's magnetic field is in Provo. In Antarctica, they're up because that's what the magnetic field is in Antarctica. Other questions? Yes.
Oh, down.
Oh, no, it's because if, first of all, I know that the magnetic field of the Earth is up. You see how I got that from this picture? Okay. And if the magnetic field lines due to my car are in the same direction as the magnetic field lines due to the Earth, they're also up. They're lined up. And so when the car gets there, I got the field lines due to the Earth and the field lines due to the car, and they're both in the same direction. So it adds. I get more. Okay. How we doing? Okay. I hope that we're going to do better on the exam. Now, yes.
So does that mean that smart light questions, wherever the car is, whether it's in Antarctica or Provo, the lines will always add in the same direction? I think.
They say the last part again?
The direction of the lines will always be additive.
Yes, the car's magnetic field will always be in the same direction as the Earth's magnetic field. And I'll make you this promise right now. I have a feeling, a strong feeling, that there will be a smart light question on the exam. Call it a premonition. Okay, or call it the Xerox machine.
The test, there could be a little confusion in magnetic north and actual.
You gotta get.
Geometric north.
Only gonna give us.
Geographic north. Yeah, geometric's different. Yeah. Well, you mean when I tell you where you are? I'm going to tell you you're in Provo, and you'll have to know where you are. Yeah. Question back here.
Yeah, if we were in trouble for this question.
Oh, that's brilliant. Thank you. What if Greg says you're at a stoplight, a smart light, on the equator in Ecuador? Okay. That question would only accomplish one thing. If it would prove Greg is truly evil. Okay, that we don't do that. Yeah. I don't even know how to answer that. At that point, it's not going to go through the loop.
Where do the magnetic field lines come in Provo again?
Oh, the magnetic field lines in Provo go towards Canada and down 70 degrees. Okay. Heading down into the pavement. Okay.
Yeah.
Now, I said there was one big idea that we needed for that exam. There's another idea that I need to
That matters.
develop to motivate that big idea. And this first idea is mutual inductance. And mutual inductance is just nothing more or less than how tightly are these two coils tied to each other. Let me see if I can explain what I mean by that. I'm gonna take this over here. And we've seen this setup before. This is the primary coil that's hooked to the battery when I close this switch. And this is the secondary coil connected to my ammeter to detect any induced current. And you see that when I close the switch or when I open the switch, I get a deflection of the needle. But it's not a big deflection because this is far apart. And remember, the current here turns this into an electromagnet, like a bar magnet, where the field lines spread out. And so if this secondary coil is far away, not many of those field lines are making it through. Now, if I bring that closer, the secondary coil, and close the switch, I get a bigger response. And the closer I get them, the more tightly those two coils are tied to each other, are coupled to each other. And I get a much bigger response. Now, there's another way to couple those coils. If I take a piece of steel and put that between the coils, even though they're far apart, I get a fairly big response, a fairly big induced current in the secondary coil. And if I bring instead a big mondo piece of iron, man, that hurts a wrist. Now you see, huge, okay? And then if I bring them close, and you see what's happening here. The primary coil is not only thinning out its own field lines, but it's magnetizing this piece of iron, turning it into a bar magnet, so that those field lines are now contributing. And that makes a huge difference. And if I have them close together with the iron core, now I think that's just huge. I think I'm going to break this thing, but I can't. It's fun. I can't stop. Feels good. Okay. Now, what we say is that those are coupled through this equation, that the flux, the number of field lines in this secondary coil, is proportional to the current in my primary coil. Okay? That if I double the current in my primary coil, I'm going to double the number of field lines that make it through this secondary coil. And whenever we have a proportionality like that, we can replace the proportionality with an equal sign as long as we include a constant of proportionality. Because this second equation says the same thing as the first equation. This equation says that if I double that, I double that. Well, if this m is a constant, then doubling this will also double that. And this constant we call the mutual inductance. The mutual inductance. Now, if we divide both sides of that equation by the current in the primary, what we get is this ratio. And I've taught you over and over again that whenever you have a ratio, something divided by something else, you set the basement equal to 1. And that's going to give you a gut feeling for what this means. What does mutual inductance mean? Well, it's the number of field lines that go through this secondary coil for 1 amp in the primary. If I put 1 amp of current through the primary, how many field lines go through the secondary? That's what it is in a nutshell. And the closer I bring those coils together, more field lines go through for 1 amp. If I put iron core in there, the more field lines go through for 1 amp. See if your neighbor understands what mutual inductance is all about.
Still never feel good. Inductance. To inductance.
Okay,
To
question,
one with.
yes.
You write in like normal language how you just explained on the board what that equation looks like?
The one on the little board or the one on the screen?
Both.
Uh, the proportionality is just saying that if I put 2 amps through this coil, I get a certain number of field lines through the secondary. But if I do twice that many, if I do 4 amps through here, I'm going to get twice as many field lines. That's what those equations up there mean. And all I've done from there to here is divide both sides by I1, the current in this guy here. And so that I did to give myself a feeling for what M was all about. How do I tell when M's big or when it's small? Well, when I put 1 amp through this primary coil with my battery, how many of those field lines from here get through to that? And if I get a lot of field lines making it through, I've got a big mutual inductance, meaning those two coils are tightly coupled to each other. Now, this is how a transformer works. Okay, with a transformer, you realize that I can increase the mutual inductance by the number of turns that are in this coil. Okay, because every turn in this coil is going to send out more field lines. And for each turn in this coil, I have to count those field lines that make it through for each turn. And so for a transformer, what I have is 2 coils that are connected with an iron core. And if I make one of those coils with a lot of turns, thousands of turns, and the other coil with only 20 turns, what that does is it steps down the voltage. When you're bringing power across the desert, you want to do it at tens of thousands of volts so that you don't lose as much energy to thermal heating. But when you get that into the city, you don't want tens of thousands of volts anywhere near your children. And so on top of those telephone poles, you have these transformers that will step down the voltage from the tens of thousands to 120 volts that's safer in your home. Okay. I don't know if that answered the question. If we go back to Faraday's law and recognize that this induced battery, this invisible battery in the secondary coil that's driving the induced current that we're seeing on the ammeter, obeys this law where the battery depends on how quickly we change the field lines through that secondary coil. Well, if we replace this flux through 2 with what it equals, well, it turns out that changing the current by closing the switch or opening the switch in the primary, that's what the 1 means, is going to generate the EMF, the invisible battery, in the secondary. And this minus sign, Lenz's law, tells us what direction it's going to generate that EMF. Now, we're almost there, people. We're almost there. Before we can go there, we need to answer this little question. If I have a battery sitting on a table, hooked through a single loop to a resistor, does bringing down the north pole of that bar magnet towards the center of that loop, does that increase or decrease the current in the loop? Those are your choices. Does it increase or decrease the current through the loop? I will get you started.
Right now. It needs to get bigger on. Want to pose that down. Need to get. A lot, but you're gonna want one spot. Just place it. To the left.
Wait, this way, it's going.
The change. They're gonna like, which is an increase.
Direction might change, but
We have to. That's where the north and south is on the map. You see. What's in the battery there? You're getting more. Fire. It's correct.
Okay,
Clockwise instead of
last call.
with the back. I know those extra.
Oh, my goodness. We're still not there, people. This is, gonna keep me up at night. The battery current, goes out of the north. I didn't say that. And if you say that I said that, I'll call you all liars, okay? Who are they gonna believe, you or me? It goes out of the positive terminal of the battery, the bumps, and folks, I keep emphasizing that the bumpy part of the battery is the positive side, because I'm an old man, and I've seen over and over again during a final exam, people missing the question because they didn't know which side was positive. The bumpy side is the positive side, okay? Trust me on this, or go home and look at a battery, okay? Now, if I bring that north pole down, as it gets closer to that loop, I'm increasing the number of field lines that are going down through the loop. Okay, fight that change. If suddenly there's more field lines going through the loop in the downward direction, I fight that change by sending field lines up through the loop. And that's going to require that it go counterclockwise. And so it would fight the battery current, and decrease is the correct answer. Okay. Okay. Questions on that?
It was going back to.
Yeah.
It's actually. Oh, and all.
I'm getting there. Patience, young Jedi. Okay. Now, what if instead of bringing the North Pole down, I brought the South Pole down? What would happen then? Yeah, then the induced current would be in the same direction as the battery current, and it would help the battery current. So I can make that induced current either help the battery or fight the battery in this situation. But there are situations where I can't make that decision. I can't change whether it's helping or fighting. And that's the case that we really want to talk about today. That's the big idea I advertised at the beginning of class. It turns out that a single coil, not two coils, but just a single coil, generates flux and fights the change in that flux. Now, we've been talking about external flux versus induced flux, but it turns out that these coils, they can't see. They don't have eyeballs. They can't tell what kind of flux it is, whether it's coming from some external thing like a bar magnet or whether it's coming from itself. They just fight any change in their flux, the flux through the coil. Okay. Now, when you have a bunch of wire in a coil, we've been assuming that the resistance of that wire is zero, that these are perfect wires. But in truth, if I get a coil from my demo room, those wires are not perfect. There is some resistance. And so when we draw a circuit diagram of that, we tend to separate out the resistance part of the wire from the inductance part of the wire. And we use the symbol capital L to indicate the inductance. Okay, so let's talk about that self-inductance. All it is, and we've been here before, is that the flux through this coil is also proportional to the current in this coil. If I double the current through this coil, I turn it into twice as strong a bar magnet, and that gives me twice as many field lines going through. Okay? And I can replace that proportionality with an equal sign as long as I put in a constant of proportionality. And in this case, that constant of proportionality, L, we call the self-inductance. And it's measured in henries, but that's just a way of honoring a dead professor. The bottom line is that it's the same thing we had with mutual inductance. It's how many field lines I get through this primary coil for every 1 amp I drive around the primary coil. And I can increase that number by increasing the number of turns in my coil. I can increase that number by putting an iron core inside of that coil. Those things would increase the self-inductance of that coil. Now, if I use Faraday's law, I get this result right here that is profound. Okay? It tells me that if I try to change the current in a coil quickly, I will generate an induced battery, an induced EMF that will fight that change. And this self-inductance here is telling me how hard it will fight. If I've got a lot of turns in my coil, it fights hard. If I've got an iron core in my coil, it fights hard. Okay? But a coil will always fight the change in current through that coil. Now, let's see what that means, what that fight means. Well, if I try to change the current through a coil from 0 to 3 amps, instantly, I close the switch right there and I want it to go from 0 up to 3. Well, look what Faraday's law teaches us. The EMF, the battery, is going to be the change in current, which from 0 to 3, this would be 3 amps. And if I do it in no time, that's 0. Plug in 3 divided by 0 in your calculator, it blows up, shrapnel everywhere. Okay, right? That's infinite. That's going to give me an infinite battery. And that tells me that this is not the way nature works. Okay? In nature, we have to ramp up the current through an inductor, a coil. Any coil, I have to gradually ramp up the current through. I shouldn't do this. I'm blinding you people. Okay? I have to ramp it up such that right here where I close the switch, right before I close the switch, and right after I close the switch, it's not that different. It's essentially zero both times. Zero both times. It takes time to ramp up that current. Okay? Check on your neighbor. See if your neighbor is following that.
That's how I do it.
You're like a needle next to the cell.
That way I can grab it with my right hand.
Okay, I have a demonstration of that here. I've got a battery on your left, okay, a 12-volt battery, and a switch here that I can push down to close the switch. And it's connected to two separate parallel branches, parallel across the battery. And on one branch, I've got two bulbs in series, and on the other branch, I've got a single bulb with an inductor with a little bit of iron core in it, just a coil, if you will. And I know what you're thinking right now. You're thinking, well, Greg, you got two bulbs on this side, one bulb on that side. That's not fair. The reason I've got two bulbs here is because we went out of our way, searched and searched high and low to find a coil that had exactly the same resistance as one bulb. And so this path has the resistance of one bulb, two bulbs, and this path has the resistance of one bulb, two bulbs. The only difference is that this is not a bulb, it's a coil. Now, when I close this switch, I want you to see what happens to these bulbs and this bulb. Okay, is everyone ready? I'm going to close it on 3. 1, 2, 3. Did you see the delay? Yeah, okay, you saw that delay. I had to ramp up that current in the bulb with the inductor. Now, some of you just learned exactly the wrong thing from that demo. And you're thinking in your mind, oh, well, Greg, over here, the current goes around and around and around and around and around. By the time it gets all the way around all those coils, that causes a delay. That's not it at all, okay? That's not it at all. You could unwind this wire and stretch it out to Springville and back in a straight line. And if you close that switch, all three of these bulbs would light up immediately. That extra 6 miles of wire is not going to change how quickly these light up. It's not the length of the wire, it's the fact that it's in a coil and it's fighting the change in current that we're trying to impose on it. Check on your neighbor, see if your neighbor's thinking wrong.
How about the coil? Right. All right.
Okay. Now, just like I can't change the current from nothing up to 3 amps instantly, I can't turn off the current through a coil instantly. Okay, I have to ramp it down. Now, I'm guessing that most of you have experienced this when you've tried to unplug a waffle iron. If you look inside a waffle iron, there's heating coils to heat your waffle, to cook your waffle. But a coil is a coil, and a coil will fight any change in the current through that coil. And when you're unplugging that waffle iron, you're trying to change the current through that coil from something down to nothing. And suddenly, those coils say, oh, no, you don't. And they throw a spark. When you pull that off of the wall, you get a spark. And that spark is the induced EMF, the induced voltage that's keeping the current going while it ramps down like that.
This power supply puts out about 6 volts. When we touch the output leads together and separate them, no spark is seen. If we hook the leads to this solenoid coil with 2,000 turns of wire and disconnect one wire, a small spark is seen. When an iron core is inserted into the coil and the sequence is repeated, a larger spark is seen.
That's still a pretty small spark, but we've seen this video a number of times. And now we're finally able to understand it, okay? They were trying to essentially disconnect the power station from the city, from the grid. And that city had transformers all over the place, coils all over the place in the grid. And by trying to take the current in that grid from something huge down to nothing, well, the city said, oh, no, you don't. Oh, no, you don't. And it threw that huge spark, which we estimated to be hundreds of millions of volts, okay, in order to keep the current going while it ramped down. Now, this suggests that there's another dangerous piece of equipment in a lab room, okay? We already said that a capacitor can be dangerous. I'm living proof of that. I'm deaf because of a capacitor. But you could charge up a capacitor, put it in the storeroom, leave it there for months, and then send a grad student in to go get it. They could grab it and pow, okay? Well, the same thing here. If you try to change the current through an inductor quickly, it can generate huge, enormous voltages to fight that change, okay? Now, I need some helpers to work this sample problem. Where are my helpers over here? Are you a helper? Thank you. Thank you. Thank you. Thank you.
Oh, I did the actual math.
Science go.
Yeah.
Oh, that section is.
We'll get on that.
Right. Just like that. Like you said.
Thomas, this group hasn't gotten any yet. I ran out. I have some of yours. Three. For you, such a deal.
Don't you?
I'll just do them all.
Have to, you know.
Now it teaches me for every single.
Okay,
Grinding.
who still needs one? Raise your hand, please, if you need one. Okay. Now, I'm again going to make a promise. On the exam, you will have a circuit that involves an inductor. Just an inductor. You will also have a circuit that involves both an inductor and a capacitor. And what we're going to find right now in this sample problem is that an inductor acts like an anti-capacitor. Whenever the capacitor is acting like a wire, the inductor acts like an open switch. Whenever the capacitor is acting like an open switch, the inductor acts like a wire, just exactly opposite of each other. So let's look at this circuit. Before I close the switch, there's no current anywhere. And after I close the switch, right after I close the switch, the current through R1 changes immediately. The current through R2 changes immediately. I can change the current through them immediately, but I can't change the current through the inductor immediately. And so that I have to ramp up. And if I'm looking right after the switch is closed, right after the switch is closed. You remember when we had capacitor problems, we always had three parts, A, B, and C. And part A was right after the switch was closed. Part B was long time after the switch was closed. And then part C was after the switch has been closed a long time, throw the switch open right after you open the switch. Those three times. We got the same three times with inductor problems. So let's look at this. Right after I close the switch, nothing can go through that inductor right after I close the switch. So it's acting like an open switch or an empty light socket, okay, if you will. Now, the questions that we've been asked here, oops. So if the current can't go through the inductor, it's got to go through R1 and R2. And so if I look at my problem, it asks, what's the magnitude and direction of the conventional current, if any, through the battery right after I close the switch? Well, right after I close the switch, the current has to go through R1 and through R2. And so if I use V equals R, where I'm using this globally, where this is the battery voltage, and this is the battery current, and this is the equivalent resistance of the circuit, well, this is going to be 200 volts, and the resistance of the circuit, since these are now in series, is going to be 45 plus 5, or 50 ohms. And that means that the current through the battery has to be 4 amps, and it's going to be up, okay, because it leaves, conventional current leaves the positive terminal of the battery. How are we doing, folks? So far, so good? Okay. Oh, you can tell this is an old problem from an old exam. What's the voltage difference? That was before I took the pledge. What is the voltage difference across the inductor? Well, if the inductor is acting like an open switch or an empty socket, I know how to deal with those. Look away from what? Look away from the sun. Look away from the sun. Okay. Look at the parallel branch. If I look at the voltage from this point A to this point B, well, the voltage difference from A to B is going to be the current that flows through that from A to B times the resistance between A and B. 45 ohms. And that's going to give me 180 volts. Now, if the voltage difference from A to B is 180 volts along this path, it's going to be 180 volts across the inductor. So the voltage difference across the inductor will be 180 volts. Does that make sense? We're still good? Okay. Now, a long time after the switch is closed, we have this equation where the voltage across the inductor, that was my EMF, is going to be minus L times the change in I through the inductor over the change in time. Now, you remember that the current through the inductor ramps up from 0 to some final value, okay? And in this case, the final value we're going to find is 40 amps. That's where I close the switch. Now, once I get up here, a long time after the switch is closed, I've got 40 amps, 40 amps, 40 amps. What's the change in current a long time after I close the switch? Nothing. And that means that this inductor has 0 volts across it. What else do you know that has 0 volts across it? A wire, a wire. And so if I wait until a long time after the switch is closed, the inductor acts like a wire. And you can just replace the inductor with the wire.
Why was it 40 amps?
Ah, hold that thought. We're coming to that. Okay. Now, so we replace this inductor with a wire.
Can't see it.
Yes, you can. Use your imagination. Okay. If this is acting like a wire now, what current's going through R1? It's shorted. All the current is now going to go through the inductor because it's acting like a wire. And now, if I look for the conventional current through the battery, I do V equals IR. And this is still 200 volts. But now the resistance of that circuit is only 5 ohms instead of 50. And that's going to give me a current through the battery of 40 amps up. That's where the 40 amps came from. Okay. Now, what's the voltage difference across the inductor? 0. It's acting like a wire. What about the current, if any, through the resistor R1? Well, that's 0 because it's shorted out. Okay. Now, did you see the parallel to what we did with capacitors? Right when I close the switch, a capacitor acts like a wire, an inductor acts like an open switch. A long time after I close the real switch, the physical switch, they trade places. The capacitor acts like an open switch and says no more charge can come, and the inductor acts like a wire. But if I wait a long time and then throw the switch, the physical switch back open, both the capacitor and the inductor act like batteries. The capacitor acts like a battery because it's charged up and you can't empty it instantly. The inductor acts like a battery because whatever current you got going through it in part B, right after I open that switch, I got to still have that current going through it because I can't ramp it down instantly. I've got to gradually ramp down the current through an inductor. So let's do part C here. After the switch has been closed a long time, it's suddenly opened. After the switch is open, what's the magnitude of the current through R1? Well, right before I opened the switch, I had 40 amps going down through the inductor. Right after I open the switch, I still have to have 40 amps going down the same direction through the inductor. But now I've opened the switch. None of the current can go this way. R2 is no longer part of the circuit. The battery is no longer part of the circuit. The circuit is now this loop right here. This loop right here. And so that means that the current through R1 is going to be 40 amps up. It's coming from the inductor. Oh, you can't see that. From the inductor. Okay, I can't change the current through the inductor instantly. Right after I open the switch, it's still 40 amps. And what's the voltage difference across that inductor? Well, that turns into a battery
Line is open now.
that is driving 40 amps through 45 ohms. And that gives me 1800 volts. And so you see, you can get a huge voltage to fight that change in current. Now, folks, I have something very important to tell you, and I want you to listen carefully. Things have not gone the way I had hoped. I scheduled some time ago to have surgery on Wednesday of next week, cochlear implants, so that I could hear you. I had that scheduled on the last day of the semester so that I could recover before spring term started. I got a call last week from the surgeon saying some equipment that we need for that surgery isn't available on Wednesday. We can only do it on Monday. So on Monday, I'm going to have surgery, which means Tuesday, they told me not to show up. They said it's going to be quite a while for me to recover. So I have created a video of review of sample problems, working sample problems, and I will send out that video link, and I will give everyone the clicker points for Tuesday. But I will try to be here on Thursday of next week, the reading day, in my office. If you have questions before the exam starts, I'm hoping that I'll be able to do that. Okay, so I love you people. We'll see you later. I really thought when I came to BYU that I was doing the Lord a solid, doing him a favor. Turns out he was doing me a huge favor by letting me associate with you. You have changed my life in marvelous ways, and I thank you for that. Go away.
Hands up, people sit back down.
When I'm like, oh, are you signing off?
Oh, bye-bye.
It's time. I thought he was going to all the protein part.